Okay, so we're going to talk today about Hess's law. And Hess's law is a way to calculate delta H. So delta H, which if you just remember this equation, right, Q equals NH, so which is the same as delta H, okay? So if you rearrange this, Q over N is just what H is. It's heat per mole, okay? So it's just like calculating Q, but per mole. Now, until now, we've been given delta H's. Like the H of fusion of water is 6.01. It's been a constant, and we've been plugging it in. So now we're going to use a different method to actually calculate the value of delta H instead of having it just be a constant, okay? So these are the really simple rules. Me telling you the rules is going to be not very helpful. The most helpful thing that we do is going to be just practicing it, okay? So, I don't know why this is.
What did you put in there to like I didn't see what you put up there.
Okay, well, we're going to practice. So I just said what delta H was. Okay, so look at this equation. Here's the whole point. I give you this reaction right here, and I say, hey, I do not know this guy's delta H. However, I have this equation and this equation where my delta H's are given. So all you're going to do is you're going to manipulate these two reactions to force them to look like the top reaction. The things that we will do will be either multiply, you can also divide, and flip things forward or backward. Okay, those are the two rules that we'll do. And you do whatever it takes to force these two reactions down here to look like this one up here. Okay, and the reason we do that is because if we know this guy's delta H and we know this guy's delta H, if we manipulate them properly, we can figure out this guy's delta H. So that's why I say it's kind of like a puzzle. You're just puzzle solving. So as I'm going through this, I'll try to teach you some strategies, okay, like tips and tricks of how to make this easier. So look at this first reactant right here. This guy's name is ethanol. That's drinking alcohol is ethanol, C2H5OH. It's an organic substance, okay? There are two of them in my reaction. So between equation 1 and equation 2, and I'm just numbering them top to bottom, all right? It doesn't really matter. Locate this species. Can you guys find it? Where is it? Where is this species down here in these two equations? It is right here. Do you see it? There's ethanol, C2H5OH. It's in that second equation. There's a problem. In this equation that I'm trying to find the delta H for, the heat of the reaction, the enthalpy of the reaction, I have two ethanols. And in my equation down here, I don't have two. I only have one. So now we have to do something. We're going to force this bottom equation to look like this equation up here, okay? How am I going to do that? Well, I'm going to take this entire equation and multiply it by the number 2. Because if I do that, I'll have 2 ethanols. That will give me 6 oxygens, 4 carbon dioxides, 6 waters. I did this only to make this match. Now here's the thing. If you multiply everything in the reaction by 2, you also have to multiply the heat by 2. You can't just leave it. If everything is doubled, you're going to get double the amount of heat or enthalpy. Okay, so sweet. I got this to match. This guy's taken care of. All right, next. A strategy right now. This species, oxygen gas, I see located in both reactions. I'm going to skip it. When you see a species in the overall reaction that you see in multiple equations down below, skip it and wait for later and cross your fingers it works out. I promise it will. Okay? So I'm going to skip that guy. Next species. This guy's name is acetaldehyde. You don't need to know that, but there it is. C2H4O. Which equation is it in? The first one, right? Do you see it? It is right here. Okay, but there's a problem. Acetaldehyde right here is a product. It is not a product in equation 1. It's a reactant. So in order to make it a product, all I'm going to do, and I'll do this up, I'll bring it up here. Actually, I'll do it this way. Let's see. I'm going to take this equation right here, and I'm going to flip it backwards. So everything on the left goes on the right, and everything on the right goes on the left. Okay? So I'm going to make it a reverse reaction. So that means four CO2 are over here, 4 water are over here. It's not the best color to write with. And then now I have 2 of the acetaldehyde, and I think it was 5 oxygens, right, on the other side. Okay? Now, if I flip a reaction backwards, I must flip the sign. So the delta H was originally negative, so now it's positive, which means if the delta H was originally positive, then you would make it negative. Here is the reason. If a reaction is endothermic one way, it is exothermic going the opposite way. They're reverse processes of one another. So that's what the reason that the sign flips. If the equation flips, the sign flips. If the equation is multiplied, the H is multiplied. You do the same thing that you're doing to the equation to the delta H. So look it, I just took care of this guy now. Now, again, I'm going to erase this up here. We are trying to get everything to match this top equation. So I'm going to go through, and in purple, I'm going to circle everything I have that's matching. So 2C2H5OH, here it is. Okay. C2H4O, there's 2 of them on the product side. Oh, good, that's what I have. Okay, good. Now we have oxygen and water to worry about. So here's how you do this. Things on opposite sides of the reaction arrow are subtractive. So if you have 5 oxygens on the right and 5 oxygens on the left, they completely cancel out. It's no net change in oxygen. So if you look at, for example, there are 6 oxygens on the left right here, and there's 5 oxygens on the right. So what does that mean? All 5 of these are gone, and 6 minus 5.
I can't see 1. It's like really hard to read.
Okay, well then you can maybe try to rewatch the video, and I'm going to do like 3 more of these. So there were 5 oxygens over on the right side. There were 5 on the right side, but then there were 6 on the left side. So these guys subtract. 6 minus 5 makes all of these gone, and we're left with the number 1, because 6 minus 5 is 1 oxygen. Oh, look, there's 1 oxygen in my overall reaction. Okay, now I'll rewrite this so it's easier to see. I'm just rewriting that. So there are 4 waters on the left side of the reaction arrow. And then down here, there are 6 waters on the other side, the right side. Things on opposite sides of the reaction arrow are subtractive. So what is 6 minus 4? It is 2, right? So that means all 4 of these are gone. Ooh, I gotta do it this way. And you're left with 2 waters on the right side, which, look at that, 2 waters on the right side overall. There's one more thing you have to do. So I've got my ethanol, I've got my 1 oxygen, I've got my 2 waters. There's a substance that we haven't dealt with yet, and it's carbon dioxide. There are 4 carbon dioxides on the left side, and there are 4 carbon dioxides on the right side. That is perfectly subtractive, meaning they're both completely gone, because 4 minus 4 is the number 0. So I completely get rid of the carbon dioxides. Now this is a good thing because my overall reaction does not have carbon dioxide in it. So we're glad that they canceled out. We don't want them in the overall reaction up here at the top right here. Okay, so now that everything matches, you combine the delta H's. So what does that mean? Well, remember this one is positive, oops, wrong color. Positive, so 2, 3, 8, 5, right here, plus, now you have to do 2 times negative 1, 3, 6, 7. So that ends up being negative 2, 7, 3, 4. That's this number. And then you just add them together. And the number comes out to be negative 349 kilojoules. Okay? So all of this I also have shown out in words on our slides. Okay? So if you look right here, this is everything I'm just doing in words and why. Okay? So we flipped one equation, we multiplied the other equation, and then we combined their delta H's to get the delta H for this equation up here that we didn't have. So again, this is called Hess's law, and the reason they call it the long way is because once you learn the shortcut way, it doesn't take as long. It doesn't take as much brain power, I guess. Okay? So again, this is everything I just did in words, so you can follow the slides as well. Notice a negative H means exothermic. So we were doing exo and endo when we were doing phase changes. Now we're doing exo and endo for actual chemical reactions. Why is it exothermic? Because the sign is negative. What does that mean? Heat is being lost, released, given off, exiting. This reaction would feel hot to us. Exothermic reactions feel hot to us, and endothermic reactions feel cold to us. Okay? So we're going to do more practice. All right. So, again, I have this reaction up here. This is the reaction I'm trying to find the delta H for. I don't know it. So what I'd like to do is manipulate reactions A and B to get it to look like this reaction, and then combine their delta H's appropriately. So, let's practice again. I have 4 ammonia. First things first, which reaction for the ammonia am I going to look at? A or B? You got to find the ammonia. It's only in one spot. Where is it? B. Okay, perfect. So, is it on the correct side of the reaction arrow? Is it a reactant? Yes. Sweet. So I got one thing going for me. But there is a small problem, because my overall reaction has 4 ammonia and the one in B does not have 4. So I'm going to force it to be 4. How do I do that? Well, how do you get 2? Oops. Yep. Multiply by 2. Good job. So you multiply everything by 2, though. You can't in math, right? You can't just multiply one thing by 2. So this now becomes 4 ammonia. This is now 6 N2O. This is 8. This is 6. And you've got to multiply the delta H by 2 as well. So I multiplied everything in reaction B by 2. And the reason I did it was to make this and this match. Okay, so like this guy's handled. Ammonia's done. Check. Okay. next, oxygen. So I go and I locate oxygen, and it's only in one spot. It's right here. So I have two problems. The first problem is the oxygen in this reaction is a reactant. And in reaction A, where I know it's delta H, it's not a reactant, it's a product. So I need it to be a reactant. The way I make it a reactant is I flip the equation backwards. So now what does that mean? Everything that was a reactant is now a product, and everything that was a product is now a reactant. So O2 plus 2N2 makes 2N2O. Now when I do this, I cross this off. I don't want to look at this anymore. It will be confusing. I just messed with it, and so you want to kind of cross it off and get rid of it so you don't get confused. Now, if I flip a reaction backwards, I also need to flip the sign. So this was negative, so now it is positive. And then, unfortunately, I'm not done because I need 3 oxygens. And I don't have 3. I only have 1. So how do I get 3? I multiply everything by 3 because that will give me 3 oxygens. So now this becomes 3. This becomes 6. This becomes 6. And then don't forget to multiply this by 3. So my oxygen is handled now. I have 4 ammonias. I have 3 oxygens. Now I'm going to try to check out my products. So I have 2 nitrogens. So I see nitrogen again in 2 different locations. It's here and here. So I'm going to look at those at the end, okay? What else? 6 waters. Oh, sweet. Look at 6 waters that are a product. That's good. So let's check out the nitrogens. Let's go back to them. There are 6 on the left and 8 on the right. So overall, that's a difference of 2 nitrogens. Okay? It'd be like you give someone $6 and then they give you 8. Okay, you end up with a change of $2. So again, things on opposite sides are subtractive. So look at, these are all gone. All 6 of these are gone. And then right here, 8 minus 6 is the number 2. Which is good. So everything in my reaction matches, but I still have to take care of one thing just conceptually. Look at this guy. Who is this? N2O. I have 6 of them on the left, and I have 6 of them on the right. So they totally cancel, right? They're completely gone. Which is good because I don't have N2O in my overall reaction. So we need them to cancel. They need to go away. So now everything is perfect. Everything down here matches. So now I will just combine my delta H's. So 3 times 164 is, so this one is 492, plus 1012 times 2, and it's negative, so this is negative 2024. Take these 2 numbers and add them together. And you get, oh, it's already on here. Negative 1,532. And again, this negative means exothermic. Heat is being lost, given off, released. Hot. You will start to notice that a lot of reactions in everyday life are exothermic. There are more exothermic reactions around us than endothermic. That doesn't mean endothermic reactions don't happen. They absolutely do happen. But things tending to want to release energy or give off energy is pretty standard. So you'll see way more exothermic processes in our everyday life than you do endothermic. Okay? This one is hard. It's not hard because it has fractions, of course, unless you're really, really bad at fractions, but hopefully I'll be able to help you. It's hard because it has a lot of equations. I'm giving you one, this is one challenge problem. The majority of your problems will not be up to this level, okay? But I do want to do one challenge one with you. So look at, we have, okay, so we're trying to find the sorry. Why are you doing that? Okay. Give me a second. So we're trying to find this guy's delta H, all right? There's going to be a lot of stuff that happens, so everybody just kind of, we're going to go slow. Again, it's not the fractions that make this hard, it's the fact that we're having to manipulate or potentially manipulate 4 different equations instead of like 2, okay? Which just, it just requires more attention, okay? So let's just start. Look at 2 boron, okay. So I'm going to go search for my boron. Do you see it? It's right here. And there's 2 of them. Oh, sweet. That guy's already taken care of. Now, here's a hint. This equation, if your 2 boron are handled and you took care of it, you better not touch this equation again. Because if you do, you will then mess up the 2 boron. So don't come back down here and touch this equation. If you have to make stuff change or manipulate, it won't be by messing with that last equation. Okay? All right. 3/2 O2. Well, that's disgusting. And I see O2 here, and I see O2 here. So my technique or my strategy is to leave those alone for now. When you see that's the species in multiple equations or multiple locations, wait to tackle them later, okay? So I'm going to ignore the O2. Fine, great. I'm going to move on to the only other chemical in this reaction, and then that's diboron trioxide. So, here it is. What's wrong with this one? It's on the incorrect side of the reaction arrow, right? So I need to flip it. So that's what I'm going to do. So everything on the left is now on the right. And I'm noticing in this reaction that there are a bunch of waters, and water is sometimes gas or sometimes liquid in here, so I'm keeping track of which waters are which because it's going to matter. Now, once I flip it, right, I'm going to like cross this guy off. I don't want to look at it anymore because it'll confuse me. And then, of course, I have to make sure I handle the delta H. What do I do to the sign? Well, if I flip it, I flip the sign, right? So now this is just negative 2035. I'm good now, right, with the B203? And you go, but there's like so much stuff everywhere. This is like a disaster, okay? So there's a couple of ways to handle this. The first way being, I see a bunch of species in these reactions that I don't have in my overall reaction. I see water, I see hydrogen, okay? What else do I see? B2H6, none of those are in my overall reaction, which means we need to force them to cancel out. We have to do whatever it takes to make them go away. And right now they're not going to go away. So here's what I'm going to say. Look at this. This reaction down here we said we liked, right, because it had the boron in it. And so I want to leave it alone. So there's many different ways to go about this right now. There's not a correct order, okay? What I'm going to say right now is I'm going to mess with the hydrogens because I don't have hydrogen up here, and so I need them to cancel. And the only way I can get them to cancel is by flipping this reaction backwards and multiplying it by 3. And the reason that it's this one I have to flip backwards because if I flip the bottom one backwards to make the hydrogens cancel, I don't have boron on the left side anymore. And that's a problem because I need it to be on the left. So I'm going to flip this equation right here, where my arrow is, backwards. I am also going to multiply it by 3. Why? Well, there's 3 hydrogens over there, which means I need 3 hydrogens to cancel. So let's do that. Flip it backwards and multiply it by 3. So let's do this. And I'm going to keep track of the water. Let's see. H2O liquid goes to H2 and 1/2 O2. Now flipping it backwards requires me to flip this sign. So this is now positive 286. Okay. And then I'm going to cross these off because I don't want them to confuse me. And then again, so okay, now I have the hydrogens on opposite sides, which is great because they'll cancel, but I need to multiply by 3. So this is a 3, this is a 3, and then this is a 3/2. Yuck, but whatever. I just say yuck because I don't personally love fractions. They're not really my favorite thing ever. Okay. So this is beautiful for right now, right? So this 3 hydrogens right here, they are gone. They cancel with these 3 hydrogens right here. Bye-bye. Wonderful. Great. I want them to cancel. Okay. I have another problem. And it's all of these waters are not working out. I see 3 waters on the left and 3 on the right, but they are not the same state of matter, so you cannot cancel them. So any suggestions on what I could do next? So this is the harder part of this problem, I think. Are you going to flip? So basically, we already flipped this equation to make the hydrogens cancel. You're not going to flip this equation to make the waters cancel because you already flipped it. Why would you re-flip it? Then you'll mess up what you were trying to do. So this one right here is the only one that I would want to flip so that I can get the water vapor on the right and then the water vapor on the left eventually to cancel. I know the numbers don't match yet, but we'll make them match, okay? So I'm going to flip this, the water-water equation backwards. So I'm going to do this in a different color so hopefully it's easier to see. So this is going to be 2H2O gas goes to 2H2O liquid. And then I'm going to flip the sign from negative or positive to negative. Now this is working out nicely because look, this is water liquid on the right and this is water liquid on the left. So we can get those to cancel as well. We need all the water gone. There is no water up here. Any suggestions on what I should do next? How do I get the 3 and the 2 to match? I'm going to multiply by a fraction. If you have 2 waters and you multiply by 3/2, you could get 3 waters. So yeah, it's a fraction and it sucks, but it would make them match, right? 3/2 times 2 is 3. Okay. What about this though? So I have the 3 water one, right? Why not 2/3? Because that would then give me 2 and then the 2's would match. Well, if you go up to this equation right here, the top one, and multiply by 2/3, you are going to mess up your B2O3. You will have 2/3 B2O3. That is a problem. We don't have 2/3 B2O3. We have one of them. So that is why I'm choosing this one, and that's why this is the only option to multiply by 3/2 to make these match. So if I multiply this by 3, that will give me 3 waters. 3 waters. Now I have 3 water vapors right here and 3 water vapors on the other side. They cancel. Now, so again, I have to multiply this by 3/2 as well. Okay? So now my water vapors that are gases, or water vapors, that's what it means. Now my water is gone. Well, 3/2 times 2 is 3 liquid waters. Oh, look, there's 3 liquid waters down here. Bye-bye. Okay. I still haven't handled the oxygens. However, B2H6 on the left, B2H6 on the right, those are gone. So now I have the 2B, I have the B2O3. Let's talk about this guy. This is 3 oxygens and this is 3/2 oxygens on the opposite side. The easiest way to look at this, for me at least, so you have 3 oxygens on the reactant side, but you have 3/2 oxygen on the product side. For me, I just rewrite this as a fraction so I can see how they subtract, right? Things on opposite sides are subtractive. Well, 3 is the same as 6/2, right? 6/2 is the number 3. So when you're subtracting, this is just easier to see. 6/2 minus 3/2 is 3/2. Oh, that helped. Look at, what is that? 3/2 oxygen. Whew. So this was a hard one. So now we're going to take all these numbers and combine them together. So negative 2035 plus, all right, this one, we split the sign and we multiplied by 3/2. So it's negative 88 times 3/2. So that's negative 132 plus 286 positive times 3. That's 858. And then we didn't touch that bottom one. We left that one completely the same, which is a 36. So negative 2035 plus negative 162 or 132, right? Sorry. Plus 858 positive plus 36, and you get negative 1,273. Again, exothermic. So that is the delta H for this reaction based on manipulating the other reactions. So in terms of this class in Hess's law the long way, I mean, this is like for this class, this is like a really hard one, okay? The majority of your homework will not be this intense.